Let's study the variation between two data sets. So we have 15 people and we collect their heights measured in centimeters and their blood glucose levels measured in millimoles per liter. So we have the following data and the data is not ordered. If you would like to, you can go ahead and transfer that into Excel and use their sort feature, but you really don't need to order it because as we can see in the equation, when we talk about variance, we have to add up a bunch of things and it doesn't matter what order you add things in. So let's just jump right into it. We've got two data sets here. Each data set has 15 points. Number one asks us to give the variance or the standard deviation of each data set, right? Because if you have one, you have the other one. Variance, you just need to take the square root of variance to get the standard deviation. If you have standard deviation, all you have to do is square it to get the variance. So let's work on number one here. The variance equation is the sum of the data minus the average of that data squared and then divided by n minus 1, where n is the number of data points that you have. So notice the order of operations here. First, I need to take each one of my data points and subtract it from the average, right? The average of the data set. I need to find the distance between each data value and the center, and then I need to square that distance. And then finally, once I have this, once I have my square differences, I will then add up all of those square differences. And then once I do that, I have to divide by n minus 1. So that's the order of operations here. So you can see that if we're going to find the variance, we need to know the average first. So let's do this. Let's work on the heights. The average height is the sum of all the heights divided by how many heights I have. So the sum of all the heights will take 65.7 plus 63.3 plus, I'm just going in the order that I have them here, all the way down the line until we run through the entire data set. 72.6 plus 56.9. And once you have that sum, you'll divide by n. Here we have 15 people. So the sum of all the height data gives you 1027.12 centimeters divided by 15, which gives us an average of 68.475 if we go out to 3 decimal places. Okay, now that we have that average, let's plug it into our equation here. So the variance, let's just write down the equation again, is the sum of the, because we're working with heights, let's call them h's. All right. So let's try to color code this. The first height that I have is 65.7. So 65.7, that's the first h in my sum. And now I find that difference from that data value, that 65.7, from my average height, which we just found to be 68.475. We'll then take that and we'll square it. Oops, don't want to use blue again. Let's go to green. We'll square it. And now finally we add all of these up, right? Because that's what the sum tells me to do. So the next height that I have is 63.3 minus the average of 68.475. I square that. And I add to this all the way down the line until I hit my last data point, 56.9 minus the average of 68.475 squared. And once I have that sum, I'll then divide that by n minus 1. We sampled 15 people, so n minus 1 is 14. Our degrees of freedom in this case is 14. So let's chase this algebra down. The order of operations says that I first have to figure out what these differences are before I square them. So let's find those differences. The first difference, the distance between my first height, 65.7, and the average of 68.475 is minus 3.0 0.056. I'll take that distance and I'll square it. And I'll add it to the next distance. 63.3 minus 68.475 gives me minus 5.465. And we'll find the distances or the differences for all of these. 56.9 minus the average of 68.475 gives me a difference of minus 11.867. Okay, now let's figure out all the square differences. So if I take minus 3.056 and I square it, I get 9.340. If I take minus 5.465 and I square it, I get 29.868. Do this for all of your data. The last square difference is 140.817. Now we find the sum of the square differences. The sum of all of this gives us 359.748 divided by, or sorry, that's just the sum. And now to find the variance, I divide that by my degrees of freedom, 14, which gives me a variance of 25.696 centimeters squared. Right, it's measured in centimeters squared because we took the differences, which is measured in centimeters, and then we squared them, and then we added them up. So we have a centimeter squared measurement. So this is my variance. I can get my standard deviation by taking the square root of the variance. So this would be the square root of 25.696 centimeters squared, which gives me a standard deviation of 5.069, now just measured in centimeters. Right, standard deviation has the same units of measurement as your original data set. Let me fix that 0, kind of looks like a 6. There we go. Okay, that's our standard deviation. So if you go through this exact same process, again, with your blood pressure, or sorry, your blood glucose levels, you'll find a variance equal to 1.639 and a standard deviation of 1.280. We're going to use this later on. But I think that satisfies condition number 1. We have the variance and or the standard deviation of each data set. Now number 2 asks, is the height of 56.9 significantly far from the average? So let's think about the person that measured a height of 56.9. So our average height, right, the center of our height data, so to speak, was 68.475. So 56.9 is somewhere over here, right? It's smaller than our average. The question is, how far away is it? The rule of thumb is 2 standard deviations. So if I take 2 standard deviations to the left of my average, so if I take 68.475 and I move 2 standard deviations away, right? If I subtract 2 standard deviations, that gives me 58.336 centimeters. So not quite over to 56.9, right? 58.336 centimeters is somewhere right here. Right, somewhere between 56.9 and 68.475. So that means that this person who has a height of 56.9 is further than 2 standard deviations away from the average. So they are significantly short compared to our sample. So it is significant. Let's do the same thing for another height. Let's see if somebody, there was an individual in our data set that measured exactly 75 inches. Is that true? Yep, there's one that says 75. So let's think about 75. or sorry, centimeters. So again, our average was at 68.475. 75 is somewhere over here. The question is it 2 standard deviations away or not? So if I take 68.475 and I add 2 standard deviations, I get 78.613. So 78 is further away than the 75. So that means 75 is closer to our average than 2 standard deviations. So this is not significant. Right? It's not quite 2 standard deviations away. All right, now number 3, use the coefficients of variation to discuss which data set has more variation. So let's summarize everything that we have so far. Let's talk about the heights and the blood sugar level. So the heights had a standard deviation of 5.069 centimeters. The blood sugar levels, so I don't want to both call them sigma. Let's say sigma sub h for heights and sigma sub b for the blood sugar levels. The standard deviation of the blood sugar levels was 1.280 millimole per liter. So just by going off of this, it seems like the heights have more variation because they have a higher standard deviation. But notice also that the heights were measured in data that the numbers were much larger than the blood glucose levels, right? The heights are somewhere between, let's say, 65 and 80. The blood sugar levels are somewhere, they're much smaller numbers, right? Somewhere between 3 and 8. So we should compute the coefficient of variation, which is the standard deviation divided by the average. And then we multiply that by 100 to turn it into a percentage, right? Because my standard deviation is measured in the same units as my average. So this quantity right here is unitless. So it's a ratio. I can multiply by 100 and it turned it into a percentage. Let's do this. So my coefficient of variation for the heights is 7.403, right? No units now. My coefficient of variation for the blood sugar levels is 24.158. Again, no units. So here we can see that even though the heights had a higher standard deviation, it's just because the data was measured with higher numbers. The coefficient of variation, how much the heights vary relative to the average, is 7.403, while the blood sugar levels vary relative to its average, 24.158%. So these are percentages. Let me put percentage signs. So there's actually more variation in the blood sugar level data than the height data.